Have you ever rubbed a balloon on your hair and watched it magically stick to the wall? Or felt a sudden spark when touching a doorknob on a dry winter day? These fascinating phenomena, my friends, are not magic, but the work of an invisible force known as electrostatic force. At the heart of this force lies a fundamental principle in physics called Coulomb's law. Coulomb's law, named after the French physicist Charles-Augustin de Coulomb, unveils the secrets behind the interaction of electrically charged objects. It's a law that governs our world in ways we often take for granted. Just like gravity dictates how objects with mass attract each other, Coulomb's law provides the rulebook for how electric charges behave in each other's presence. Coulomb's law is not just an abstract concept confined to textbooks. It's a fundamental truth that underpins countless technologies we rely on every single day. From the smartphones in our pockets to the medical imaging devices used in hospitals, Coulomb's law is the silent conductor orchestrating the flow of electrons that powers our modern world. The universe is a fascinating dance of particles, and at the heart of this dance lies the interplay of fundamental forces. Among these forces, the electromagnetic force, particularly its electrostatic component, plays a starring role in shaping the world as we know it. But why, you might ask, is understanding the force between charges so crucial? The answer lies in the very fabric of our existence. Atoms, the building blocks of matter, are composed of charged particles, positively charged protons nestled within the nucleus, and negatively charged electrons orbiting around it. It is the electrostatic force of attraction between these opposite charges that holds atoms together, giving rise to the elements and molecules that constitute everything we see and touch. But the influence of electrostatic forces extends far beyond the atomic realm. They dictate the behavior of matter on a macroscopic scale, influencing everything from chemical reactions to the functioning of our brains. Understanding these forces is not just about deciphering scientific curiosities, it's about unlocking the secrets of the universe itself. Coulomb's law, like many fundamental laws of physics, can be expressed elegantly in a mathematical formula. Don't let the equations intimidate you. They are simply a concise and powerful way to describe the relationship between different quantities. In the case of Coulomb's law, the formula tells us how the force between two charges is determined. The formula for Coulomb's law is F equals K times the product of Q1 and Q2 divided by R squared. Let's break it down piece by piece. F represents the electrostatic force between the two charges. Q1 and Q2 represent the magnitudes of the two charges. R is the distance separating the charges. And finally, K is a constant known as Coulomb's constant, a value that ensures the units in the equation work out correctly. This formula reveals some important insights. First, the force between two charges is directly proportional to the product of their magnitudes. In simpler terms, bigger charges exert stronger forces. Second, the force is inversely proportional to the square of the distance between the charges. This means that as charges get farther apart, the force between them weakens rapidly. Section 4 vectors mapping the direction of the electric force. While the mathematical formula for Coulomb's law provides the magnitude of the electrostatic force, it doesn't tell us everything. Force, you see, is a vector quantity. To fully grasp the interaction between charges, we need to consider both the magnitude and the direction of the force. This is where vectors come in. Imagine two charges, one positive and one negative. We know they attract each other, but in which direction does the force act? The answer lies in the concept of electric field lines. These imaginary lines emanate from positive charges and terminate on negative charges, providing a visual representation of the electric field. The direction of the electric field at any point indicates the direction of the force that would be exerted on a positive test charge placed at that point. For opposite charges, the field lines point directly towards each other, signifying an attractive force. For like charges, the field lines point away from each other, signifying a repulsive force. Section 5, Attraction and Repulsion. Examples of Coulomb's law in action. Coulomb's law beautifully explains the phenomenon of attraction and repulsion between charged objects, a fundamental concept that shapes our world in countless ways. Let's delve into some examples to see how this law manifests in everyday scenarios. Consider the simple act of rubbing a balloon on your hair. As you rub, electrons are transferred from your hair to the balloon. giving the balloon a net negative charge and your hair a net positive charge. Now, when you bring the balloon near your hair, the opposite charges attract each other, causing your hair to stand on end as if pulled by an invisible force. Now imagine bringing two balloons that have both been rubbed on your hair close to each other. This time both balloons carry a net negative charge. As you bring them together, they will push away from each other. This repulsion occurs because like charges repel. Section 6. A tale of two forces, comparing Coulomb's law and gravity. Coulomb's law, which governs the interaction between charges, might seem reminiscent of another fundamental law of physics, Newton's law of gravitation. Both laws describe forces that act over a distance, but there are crucial differences between these two fundamental forces. One key difference lies in the nature of the forces. Gravity is always attractive, pulling objects with mass towards each other. Coulomb's law, on the other hand, describes both attractive and repulsive forces depending on the signs of the charges involved. Like charges repel, while opposite charges attract. Another difference lies in the relative strengths of the forces. While gravity is the dominant force on astronomical scales, holding planets in orbit and galaxies together, it is remarkably weak at the atomic and molecular levels. In contrast, the electrostatic force is incredibly strong, far surpassing the force of gravity at these scales. Section 7. Coulomb's law in our lives, from touchscreens to medical marvels. Coulomb's law might seem like a concept confined to the realm of physics textbooks, but its influence extends far beyond the laboratory. It underpins countless technologies that have revolutionized our world, shaping the way we communicate, receive healthcare, and interact with the world around us. Take, for instance, the touchscreen device you're likely reading this on right now. Touchscreens rely on the principle of capacitance, which is directly related to Coulomb's law. When you touch the screen, your finger alters the electric field between the conductive layers within the screen, registering the location of your touch. In the medical field, Coulomb's law finds applications in technologies like electrocardiograms, or EKGs, and electroencephalographs, or EEGs. These devices measure the tiny electrical signals generated by the heart and brain respectively, providing invaluable insights into the functioning of these vital organs. Coulomb's law helps us understand and utilize these electrical signals, paving the way for life-saving diagnoses and treatments.